Hello, we are Team DeFT. Let us start presentation about our final project. First of all, we have reviewed through some feedbacks from last peer review. Starting with the first one, since our objective is to construct a robust deep learning algorithm with small dataset, using deep learning model would be limited. That's why we are focusing on using the machine learning algorithm. To deal with the problem of the third feedback, we used a blur dataset including ground truth images for performance evaluation and added some images taken by our own. About the question about kernel separation, we will discuss this later on. Let us briefly review our project topic. We were focusing on single image deblurring, and this can be computed by implementing a convolution operation with a deblur kernel. So this problem can be simplified into estimating a deblur kernel. The main idea is to estimate a probability of the deblurred image and filter, which can be calculated simply by Bayes' theorem. Likelihood and prior we used here is shown in the slide. Also, overall deblurring process is shown as a pseudocode here. To optimize the final deblurred image L, we repeated iteration until psi and L matrix converges.
At first, we tried to combine two small kernels to analyze both camera blur and subject motion blur. However, as you can see, the result contains a lot of noise and the separation seems to be failed. Therefore, we changed our method from separating blurring into two small kernels into using one big-sized kernel. After increasing the blur kernel size to 35 by 35, this is our deblurred image result. The deblurring and kernel estimation seems to be working somewhat well. However, there were some problems to solve in this method, including the long iteration time and initial kernel guess dependence. As observed in the deblurred images and kernel images, kernel divergence and noise were identified, which leads to degradation in deblurring performance. To address this issue, we trained an initial kernel to achieve better deblurring performance.
To find the kernels that transforms the latent image to the blurred image and the blurred image to the latent image, we use the equation below to obtain the optimal kernel for each case. For training, we got a motion blurred image dataset with ground truth from Kaggle. From the image dataset, we formulated the corresponding Fourier approximated kernel and inverse kernel. By adding the kernels into the original dataset, we created a valid dataset for the neural network to learn. Images reconstructed by the obtained Fourier transform is shown above. By the above image, we can conclude that the kernel we obtained is valid.
Training deep neural network with 350 images was not enough. For efficient training, we generated motion blur in various directions with our own photos using Kernel module. Since the goal of the project is to deblur images in a low data situation, data augmentation was applied to only 150 images. To have consistency with real blur data, we use Fourier transform estimated kernel rather than the actual kernel used for the generation. After all the pre-processing, we aggregated the dataset into single annotation as below. This dataset was used to train our neural network. We jointly trained the two networks which predict the blur kernel and the reverse kernel for initialization using the above losses. During the test time, the kernel output of the neural network is used as the initial kernel of our deblurring algorithm. Our neural network is composed of two parts. The confident part estimates the kernel that transforms the blur image into the latent image. The predicted blur kernel is then fed into the unit architecture where it outputs the estimated inverse of the kernel f theta. It is then compared with the kernel in the dataset f star, so that the estimated kernel is regularized as an invertible matrix. Notice that after the kernel is applied, the line of property of the trained images and the estimated images are well shown. This implies that the predicted kernel captures blur direction properly. We can utilize this kernel as a starting point of our algorithm.
Now it is time to evaluate the images. For performance evaluation, we use HSV histogram comparison from the CV2 library to evaluate how much the deblurred image matches the original image. Comparing both the execution time and total evaluation score, end-to-end deep learning showed the best result. However, considering the noise pattern, the kernel deblurring methods showed an intuitively better image. Between the two kernel methods, you can check that the kernel training shortened the execution time and brought an enhancement of deblurring. These are the deblurring results for with and without kernel initialization and end-to-end deep learning. You can check that the score for the initialized kernel has improved. However, there is not a significant difference for a naked eye between the two metrics. This is a comparison between our deblurred image. You can see the significant improvement.
To assess the performance of our model, we used end-to-end deep learning model. Deep learning model achieved the highest evaluation score, but ringing artifacts are still observed. Using a small dataset for training leads to overfitting, which manifests in the appearance of ringing artifacts. Our method using training initial kernel was able to deblur better than the previous attempts. The picture on left is the initial kernel estimated by our model. Motion blur pattern referring top left is observed. Our hypothesis that using a pre-trained kernel would improve the deblurring found out to be valid and reasonable. Lastly, we've made some recommendations that can improve the shortcomings of this project. Thank you for listening.